Hi friends, in this video lecture we are going to study LU decomposition of a matrix, in which we are going to see definition of the LU decomposition, some application, some problems and existence of a LU decomposition of a given matrix. So now let's first see what is an LU decomposition of a matrix. So let A be a square matrix, it's a square matrix of order n cross n. Then A can be written in the form, or it can be decomposed as a product of two matrices LU, where L is a lower triangular matrix, lower triangular matrix, and U is an upper triangular matrix. Okay, even this A can be written as a product LU, where U is a lower triangular matrix with diagonal entries as 1. Similarly, we can also write A as a product of, or even similarly we can decompose A as a product of matrix LU, where L is a lower triangular and U is a upper triangular, where the diagonal entries of U are fixed as 1. Okay, so let's quickly revise. So A is a square matrix, so it can be decomposed into a product of two matrices, which is LU. L is a lower triangular matrix and U is an upper triangular matrix, or even it can be written as a product of two matrices where L is a lower triangular and U is an upper triangular, where L, the diagonal entries of the matrix L is 1, all the diagonal entries, or it can be, or A can also be decomposed as an LU, where all the diagonal entries of U are 1. Some applications of LU decompositions are: first, computer system uses LU decomposition to find a solution of n linear equations in n variables. Second, you can answer whether the inverse of a matrix exists or not by looking at the LU decomposition. Third, you can quickly calculate determinant with the help of LU decomposition. Now let's consider an example of finding LU decomposition. So A matrix is given, which is a 3 cross 3 matrix. So now we are going to find LU decomposition of this matrix by using Gauss elimination method. That is nothing but by using our standard row operations. So now what we are going to do, we are going to reduce this A matrix into the upper triangular matrix. So the first step, which is going to be, we are going to make this element 0, okay, by using row operation. So what are the row operations are involved? We changes R2 changes to R2 minus. Now you write this coefficient in bracket, whatever the coefficient comes out, because this coefficient will help us to generate lower triangular matrix. Okay, so it's a R2 changes to R2 minus. The coefficient of R2 is 1 and the coefficient of R1 is 2, so it's going to be 1 by 2 R1. Then this is for the second row. For the third row, it's going to be R3 changes to R3 minus. Again, I think it's going to be 1 by 2. I'm writing in bracket. It's going to be R1. Okay, so by these two operations, the entries which are circled is going to get changed to 0. Okay, so now let's see what matrix we are getting. So the first row is going to is not going to get changed, so it's a 2 4 minus 6. This R2 operation is going to be 0. Next is a 5 minus 2 is going to be 3. Then it's a 3 minus 6, so it's going to be plus 6. So answer is going to be 6. Then next, again this entry will become 0. Then we have 1. Then we have 5 by using R3 operation. Now next, we are going to make this element as 0 by using R2, which is the pivot element. So now R3 changes to R3 minus the coefficient and we are going to use the R2. So what will be the coefficient? R3 is nothing but 1 divided by 3 because R2 coefficient is 3 or the R2 entry is 3. Okay, so now let's see what happens. So the matrix gets changes to 2, 4, minus 6, 0, 3, 6, 0, and the next entry again it becomes 0, and then the last entry it's a 5 minus 2, so it's a 3. So this is going to be our upper triangular matrix U. Okay, this is going to be our upper triangular matrix U. So now let's see how to get L. It's very easy, as by the brackets that I highlighted while writing the row operation that will help us to quickly get the lower triangular matrix. We are going to fix the diagonal entries as 1. Okay, we are taking diagonal entries as 1, and the above that we are taking it as a 0 because it's a lower triangular matrix. Now the first operation, we have used this means R2 changes to R2 minus 1 by 2 R1 to make these entries as 0. So at this place you write the coefficient of R1, which is nothing but whatever is written in the bracket, which is 1 by 2. So here it will be 1 by 2. Next, R3, we have used this row operation to make this entry as 0. So what is a coefficient or what is there in the bracket? It's a 1 by 2. So again here it's going to be 1 by 2. Next, we have used this R3 operation to make this entry as 0, and again in bracket we have 1 by 3, so here it's going to be 1 by 3. Now one can actually quickly check, if you multiply L to U, you will get A. So this is one of the standard way of calculating LU decomposition of a matrix. So now let's consider another example where A is a 2 cross 2 matrix. So now let's apply the same similar row operations as in the previous example. So here we are going to change R2. We are going to make this element as 0 because we are going to convert A into in the upper triangular matrix. So R2 changes to R2 minus something will come in the bracket, and then we are going to use R1. So what is the coefficient of R2? It's going to be minus 2 and then divided by the entry of R1, which is 3. Okay, so let's see what is our new matrix. So the first row is going to be same, it's a 3 minus 6, and the another one here is going to be 0, and then here we are going to get it as 1. So very quickly we got the upper triangular matrix U. So now we can use the row operation to get the lower triangular matrix. So the lower triangular matrix is, the diagonal entries are 0, above diagonal entries it's going to be diagonal entries are 1 and the above diagonal entry is 0, and then we have used this row operation to make this value at 0. So the coefficient what is there in the bracket, it's a minus 2 by 3, so here you put it as minus 2 by 3. So this is your LU decomposition of the given matrix. One can use this formula to get LU decomposition of a 2 cross 2 matrix. Once you identify the value of A, B, C and D, you can directly substitute here. You will get the L matrix and you will get the U matrix. For 3 cross 3 matrices, one may consider this A matrix is equals to L into U, where L you can see it's a lower triangular matrix where the diagonal entries are fixed as 1 and U is an upper triangular matrix. And then multiplying this L into U, you will get some system of equations, and then by some calculation you will get the values of all these entries L21, L31, L32 and the entries of U. This is also a way of calculating LU decomposition of a given matrix by forming a system of equations. Now the question arises whether LU decomposition exists for every square matrix A. Definitely, if one sees the above formula of finding the LU decomposition of a 2 cross 2 matrix, it's easy to understand that if A is 0, then this value C by A won't be defined. Okay, here in the upper triangular, again it's here A is occurring in the denominator. So the answer is not every matrix A has a LU decomposition, or you can say not every matrix A can be decomposed as a product of lower triangular and an upper triangular matrix. So now let's see an example of that. Now consider this matrix A, which is a 2 cross 2 matrix with entries 0, 1, 1, 0. This matrix A cannot be decomposed into a product of two matrices where LU, where L is a lower triangular and U is an upper triangular matrix. So now let's consider, let's try to find LU decomposition of this matrix. So suppose we take it, this A matrix equals to L11, 0, L21, L22, U11, U12, 0, U22. So when we multiply this matrix on the right hand side, we get as L11, U11, L11, U12, then U11, L21, L21, U12 plus L22, U22. So after multiplying this, we get this matrix. After multiplying L into U, we get this matrix. So now by comparing, we get that, means comparing this matrix with the A matrix. So we get that the first entry L11 into U11 is equals to 0. And if I see this entry means the second row and the first column, so we get U11 into L21, which is equals to 1. So the first, and even we can consider this entry, which is L11 into U12, which is equals to 1. So now if I see first one, which is L11 into U11, it says that one of them has to be 0. So if we take L11 as a 0, that will be a contradiction to the last equation, because L11 into U12 is 1. So L11 cannot be 0. So if we take U11 to be 0, so then that's a contradiction to the second equation. So this implies that this system of equations doesn't have a solution, which says that A cannot be decomposed as a product of two matrices where L is a lower triangular and the second is an upper triangular matrix. So this theorem gives the sufficient condition for a matrix to have a LU decomposition. So if A n cross n matrix can be reduced to a row echelon form without interchanging rows, then A has a LU decomposition. So now we saw that every matrix cannot have a LU decomposition, but every matrix A can be written as a product of LU into P, where P is a permutation matrix. Where L is a lower triangular and U is our upper triangular matrix. Every matrix A can be written as a product of these three matrices where L is a lower triangular, U is an upper triangular, and P is a permutation matrix. Permutation matrices are those matrices whose entries are only 0 and 1, and every row contains only 1, 1 and others are 0, and every column contains only 1, 1 and other entries are 0. So suppose if we have a matrix A which doesn't have a LU decomposition. So what we are going to do, we are going to perform some permutation with the rows of A such that that matrix can be reduced to the row echelon form without interchanging rows. Means before we just interchange the rows of A, then when we convert into the row echelon form, we are not interchanging its row. Basically, then it satisfies the condition, means the matrix PA satisfies the condition of the above theorem, that the matrix can be reduced into the row echelon form without interchanging the rows. Okay, so then this PA can be decomposed as an LU, and P is a permutation matrix, so its inverse is also a permutation matrix. So then we can write our matrix A as an LUP inverse, and then we get the decomposition of A. You can take this example for practice to find LU decomposition of the matrix. Thank you.